Torch autograd is Pytorch's automatic differentiation engine that powers neural networks training. In this section, you will get a conceptual understanding of how autograd helps a neural network train. Okay, background. Neural networks are a collection of nested functions that are executed on some input data. These functions are defined by parameters consisting of weight and biases, which in Pytorch are stored in tensors. Training neural networks happens in two steps. Forward propagation. In forward prop, the neural network makes its best guess about the correct output. It runs the input data through each of its functions to make this guess. In back propagation, the neural network adjusts its parameters proportionate to the error in its guess. It does this by traversing backwards from the output, collecting the derivatives of the error with respect to the parameters of the function gradients, and optimizing the parameters using gradient descent for a more detailed walkthrough of backprop. Check out this video from 3.1 round, and I think I already done this, right? I think I did some time ago. We might go and see this video maybe later, or maybe not. I don't know if that's okay. So for now, we're going to go through this. Going to grab a text here and say training, and this is like a rough note, right? Doesn't need to be what you do. Forward propagation. Let's put here guess slash prediction, and two. I wrote this bad. Forward and backward propagation. This is adjusts to fit better the data using gradient of functions and gradient descent algorithm. All right. Yes. So, usage in Pytorch. Let's take a look at a single training step. For this example, we load a pre-trained ResNet 18 model from Torch Vision. We create a random data tensor to represent a single image with 3 channels and a height and a width of 64, and its corresponding label initialized to some random values. Okay, let's try that. Import Torch Vision module, Torch Vision modules, ResNet 18. I said 18. Shoot. Okay. Pre-trained is equal to true. Sorry, it's already trained. Well, great. Just the letter says, and so you have here sort of a data set. I already saw this in some places. Like we have one example of a 3 by 3 channels of 64 and 64, height and width, right? Height and width. Yes. Rows, columns. And labels, Pytorch, random 1 to 1000. We run that, and that's awesome. Next, we run the input data through the model through each of its layers to make a prediction. This is the forward pass. So we make prediction model data. And we have nothing. Use the model predictions and the corresponding label to calculate the error loss. The next step is to backpropagate this error through the network. Backpropagation is kicked off when we call backward on this error tensor. Autograd then calculates and stores the gradient for each model parameter in the parameters.grad attribute. That's a lot there. That's a lot there. So let's note this in the notebook. Okay, I think that's important. So we make a loss in this example, predictions minus labels dot sum, and then we grab that and we go backwards. So what is the prediction here? Let's see that. Prediction is a huge tensor of probabilities, right? And we have here grad function add backward something. Let's delete this. And this is the backward pass where the backpropagation is doing the job. Okay, let's see. Next, we load an optimizer, in this case stochastic gradient descent, with a learning rate of 0.01 and momentum of 0.9. We will register all the parameters of the model in the optimizer. So optim equal to torch.optim stochastic gradient descent and model parameters, learning rate 1e -2, momentum 0.9. Great. Now, so this is going to calculate the loss, and the loss backward is going to calculate and store the gradient for each parameter in the parameters.grad attribute. So this here is going to calculate the gradient, and this is going to go to the direction of the gradient and update to a better position. When we do, finally, we can go dot step to initiate gradient descent. The optimizer adjusts each parameter by its gradient stored in .grad. That is when we do this. So optim dot step, and it did something. At this point, you have everything you need to train your neural network. The Velox sections detail the workarounds of autograd. Feel free to skip them. Oh, we're going to read this. Okay, let's read this. And it says, differentiation in autograd. Let's take a look at how autograd collects gradients. We create two tensors A and B with requires grad true. This signals to autograd that every operation on them should be tracked. Okay. Let's make a distinction here. So we have Pytorch, A, torch the tensor, 2, 3. God damn it. Let's copy this. And 6, 4. Oh, it should be small b. All right, small b. We create another tensor Q from A and B. So Q, I don't know why this is so small, but this says Q equal to 3 times A to the third power minus B squared. So Q equal to 3 times A over 3 minus B squared. Shift Q, and we have that. So let's see what that is. This rising power is, I think, is each element. It's an element-wise thingy. Let's assume A and B to be parameters of an error neighborhood, a Q to be the error. In NN training, we want gradient of the error with respect to parameters. So yeah, this is a little bit small, man. I don't know, maybe it's the browser. I'm thinking, well, it doesn't matter. This is the little bit of calculus. Since we have two variables here, this is the first, the derivative with respect to the first parameter, and this is the derivative with respect to B, the second parameter. So when we call the backwards on Q, autograd calculates these gradients and store them in the respective tensors dot grad attribute. So if we go Q dot grad here, it says a lot of things. It says who's surrounding the dot grad attribute of the tensor. There is not a leaf tensor being accessed. Its dot grad won't be populated during autograd. If you indeed want to also use retain grad on the non-leaf tensor. Okay, a bunch of things. We're going to continue reading this. So when we call the backwards, I think I already read that. We need to explicitly pass a gradient argument in Q backward because it is a vector. Gradient is a tensor of the same shape as Q, and it represents the gradient of Q with respect to itself. Oh, maybe this is the why this is yelling at me. External grad. I'm going to read that again. I didn't quite get it. We need to explicitly pass a gradient argument in Q backward because it is a vector. Gradient is a tensor of the same shape as Q, and it represents the gradient of Q with respect to itself. Equivalently, we can also aggregate Q into a scalar and call backwards implicitly, like Q.sum.backward. Thinking of that, alright, we maybe can note this here. Pytorch tensor Q dot backward gradient equal to external grad, and I did an oopsie here, another oopsie. Let's copy this to be the same. The other way around. Awesome, we have that. Check if collected gradients are correct. So now we're using the formulas of the derivatives. Maybe you can see this, but it says 9 times a squared. That is the derivative of this first term here, and 2b, so minus 2b. Let's see. Let's copy this because we don't learn anything by trying, and we only last time. So it is true. Awesome. So we learned that the backwards generates the derivatives of the vector, this vector. There's something I didn't quite understand, but we need to give it an external gradient so it can populate that. Or we can also do this. So let's see what that looks like. So qsum dot backward okay, we're doing something that we are not supposed to do here, apparently. So we might need to sort this later on. Trying to backward through the graph a second time, but the same intermediate result have already been freed. Specify retain graph true when calling backward the first time. Alright, so we learned something. If we call 2 times in a second time the backwards in the same vector, we can't do that. There is an exception or an error. Oh shoot. Awesome. Now, what's up here? Optional reading vector calculus using autograd. Ooh. Okay, let's take a look at this. Then exclusion from the DAG. Okay. Gonna drink some water. Alright, so where are we? Let's read this, but let's not get that into it because maybe it's a little bit too too advanced for us. Mathematically, if you have a vector value from, it says yfx, then the gradient of y with respect to z, it's a z, it's a Jacobian matrix J. Holy, yeah, this is pretty advanced. I'm gonna try something. Maybe can do. Let's see if Firefox displays this better. It doesn't. They just. Their thingy is a little bit broken. Generally speaking, Torch autograd is an engine for computing vector Jacobian product. This is given by any vector B compute the product GT minus B, I think it says. B, if B happens to be the gradient of a scalar function, that then by the chain rule, the vector Jacobian product will be the gradient of I with respect to Z. This characteristic of vector Jacobian products is what we use in the above example. External grad represents B. Okay, I didn't quite understand this. We might need to read this again. It's a little bit advanced calculus, maybe. I know this because I did a course of calculus in university, so I know this is advanced. So we're not going to stay here longer. All right. So computing graph. All right, this is important because we have just an error with the computing graph. So we're going to say computational graph, and it says conceptually, autograd keeps a record of data, tensors, and all executed operations along with the resulting new tensors in a direct acyclic graph. A DAG. Oh, of course, DAG. I remember now what DAG is. Directed acyclic graph. Remember that. Consisting of function objects. In this DAG, leaves is like leaves. Hold on. My English. Oh yeah, leaves. Like 3 leaves. Leaves are the input tensors. Roots are the output tensors. By tracing this graph from the roots to leaves, you can automatically compute the gradients using the chain rule. In a forward pass, autograd does 2 things simultaneously. Run the requested operation to compute our resultant tensor and maintain the operation gradient functions in the DAG. Okay, let's know that. What autograd does. Forward pass does 2 things, right? I'm gonna do this. Why it doesn't? I need to do that. I'm going to make this bolder. I say bolder. Great. run operations to compute resulting tensor to maintain the operations gradient function in the DAG. And in the backward pass kickoff when dot backwards is called on the DAG root. Autograd then computes the gradient for each dot grad function fn, accumulates them in their respective tensor dot grad attribute, and using the chain rule propagates all the way to the leaf tensors. Alright, so we have compute the gradient from h dot grad function, accumulate them in their respective tensors dot grad attribute, and 3, using the chain rule, propagates all the way to the leaf tensors. It's awesome. Padam pam padam padam pam dice. Padam padam da da. Below is a visual representation of the DAG in our example. In the graph, the arrows are in the direction of the forward pass. The nodes represent the backward functions of each operation in the forward pass. The leaf nodes in blue represent our leaf tensors A and B. Quite a paragraph there, so let's read it again. Below is a representation of the DAG in our example. In the graph, the arrows are in the direction of the forward pass. The nodes represent the backward function of each operation in the forward pass. The nodes. These nodes, right? And the leaf nodes in blue represent our leaf tensors A and B. A and B, power backward, mult backward, backward, sub backward. All right. Give me a moment here. All right. What the note says. DAGs are dynamic in Pytorch. An important thing to note is that the graph is recreated from scratch after each dot backward call. Autograd starts populating a new graph. This is exactly what allows you to use control flow statement in your model. You can change the shape, size, and operations at every iteration if needed. Right? It's a really cool node, so you're going to know that. And give it a B here. Great. Exclusions from the DAG. Torch autograd tracks operations on all tensors, which have their required grad flags set to true. For tensors that don't require gradients, setting this attribute to false excluded it from the gradients computational DAG. The output tensor of an operation will require gradients. Again, I lost there. The output tensor of an operation will require gradients even if only a single input tensor has required grad true. Okay. So Z requires autograd, requires the gradient. A and X and Y doesn't. So A is equals plus Y. So it doesn't require here. And B is X plus Z. So Z does require the grad. So the output is that B does require. Awesome. Let's see here. In a network, parameters that don't compute gradients are usually called frozen parameters. It's useful to freeze part of your model if you know in advance you won't need the gradient of those parameters. This offers some performance benefit by reducing autograd computations. Let's note this. I think it's really cool. All right, so another common use case where exclusion from the DAG is important is for fine-tuning a pre-trained network. In fine-tuning, we freeze most of the model and typically only modify the classifier layers to make prediction on new labels. Let's walk through a small example to demonstrate this. As before, we load a pre-trained ResNet 18 model and freeze all the parameters. Let's write this as also this is for fine-tuning pre-trained networks. We might be looking at this in the future. This looks interesting. So that's really cool. Let's see the small example here. So let's start from the beginning, from Torch, import NN and Optim. You had the model, Torch Vision models, ResNet 18, pre-train, go to true. So we freeze all the parameters in the network. For param in model parameters, param requires grad equal to false. I will run this. Awesome. So let's say we want to fine-tune the model on a new dataset with 10 labels in ResNet. The classifier is the last layer, layer mul FC, fully connected, I think that is. We can simply replace it with a new layer, unfrozen by default, that acts as our classifier. Okay, so model.fc equals to nn.linear 5, 12, 10. DWC. All right. Now, all right. You have it all. Now, all the parameters in the model except the parameters of model FC are frozen. The only parameters that compute gradients are the weights and bias of model FC to the last layer. Optimize only the classifier. Also, we give the optimizer stochastic gradient descent. We give only the parameters of the last layer. This is a term model, so this is doesn't really matter, I think. Yes. Notice, although we register all the parameters in the optimizer, the only parameters that are computing gradients and hence updated in gradient descent are the weights and bias of the classifier, the last layer. The same exclusionary functionality is available as a context manager in Pytorch autograd. The same exclusionary functionality is available as a context manager in Pytorch autograd. Didn't quite understand this, but that's alright. We're going to put it here. See this one, and this is the docs. So we might, let's see what this says. Context manager that disables gradient calculation. Disabling gradient calculation is useful for inference. When you are sure that you will not call tensor backward. It will reduce memory consumption for computation that will otherwise have required grad equals to true. Okay, so it means that doing this ignores requires grad true. In this mode, the results of every computation we have require grad false, even when the input have required grad true. This context manager is thread local. It will not affect computation in other threads. Also functions as decorations. Also functions as a decorator. Make sure to instantiate with parentheses. Example, Pytorch autograd return R. So this is decorator using this here.